Okay, today we're going to review the exponential and logarithmic problems. And so let's start with our first one. Here we have 2 to the x minus 3 equals 8. And for these types of problems, this is where we focused on trying to get the same base on both sides of our equation. And notice 2 is already a good base that we talked about. And over on the other side, we would change 8 to be 2 to the third. And now that we have our bases the same, we do set our exponents equal to each other and solve for x. And notice that we do end up with x equals 3. Moving on to the next problem. Same process. Now this time we do have to look at 5 is going to be our good base. And so this side over here already has everything lined up like it should, 1/2 x plus 4. But over on this other side, we will need the reciprocal of 1/5. So that means I need 5 to the negative 1. So our equation is equal to negative 1. We are going to subtract 4 over to the other side, so that's going to give me negative 5. And now I need to multiply both sides by 2. So x is equal to negative 10. Okay, for number 3, it looks like we need to get a base of 3. So here for the first one, 9 is 3 squared. But then we don't need to forget that we already have an exponent of 4x minus 1. And then over on the other side, 27 would be 3 to the third. So here, now that we have our bases the same, we do need to do our distributive property. So we're going to get 8x, need to fix that. We're going to get 8x minus 2 equals 3. And so solving for x, we do need to add 2 over to the other side. And so x is going to be 5 over 8. For number 4, we need to look at 8 and 64, and we do need to change our base all the way down to 2. So 8 is 2 to the third, and we still had our exponent of 3x minus 2. We don't need to forget that. Is equal to, now 64, that's going to be 2 to the 6th, but we're going to make it negative 6 so that we get the reciprocal of 1 over 64. Now we have our bases the same. We do need to multiply our exponents, so that's going to give me 9x minus 6 equals, and the same is true over here. So I have negative 6 plus 6x. And if we subtract our 6x over, we have 3x minus 6 equals negative 6. And we would need to add 6 over. So 3x equals 0. So it looks like x is 0 for this problem. Alright, so on number 5, we're going to change 4. That's going to be 2 to the second. And that is still times our 1 minus 3x that's there. Equals, now we have to remember to change this. There's an understood 1 there. And so 2 is going to be to the 1 over 3, or 1/3. And now we have our like bases, so we're going to have 2 minus 6x equals 1/3. And if you wanted to remove that fraction, if you don't want to deal with fractions, we can multiply every part by 3. This is just if you want to. Some people would rather remove that fraction and work with, I put a 6x there. Goodness, let's back up. So it's going to be 6 minus 18x, sorry about that, but a lot of times people will choose to remove the fraction, and do keep in mind that does cancel, leaving 1. And so here we have negative 18x equals negative 5, so x is going to be 5 over 18. Moving on to number 6. Now in this case we have 9 to the 5 minus 2x, and if all of that is equal to 1, keep in mind that really we could change that 1 that would be the same thing as 9 to the 0 power. And that way we have our like bases. So I'm going to say 5 minus 2x has to be equal to 0. That's the only way you're going to get all of this side to change to be just a 1. And now solving this, we're going to subtract 5 over and divide by negative 2. So x is 5/2. Now we will be reducing our logarithms, and these all would be non-calculator, so we do need to know how to simplify these. And in class we talked about having a shorter way of doing these, where we said our base, that's really 2 to the first, 16 is really 2 to the fourth, and so our simplified version would be 4 over 1, which is 4. Okay, moving on to number 8. We're still going to follow that same process. We are going to get our base of 3. So I have log, and 9 is 3 squared, 27 is 3 cubed, and so our nice little shortcut here tells us this will reduce to be 3/2. And the same for number 9. Number 9, we have log base 32, which is 2 to the 5th, and 2 to the 1/2 is going to be square root of 2. And so when we put this together, that's going to be 1/2 over 5, and that's going to be 1/2 times this reciprocal, 1/5, and so we get an answer of 1/10. So for number 10, what we need to do is focus on this first part and think about this as 6 times log base 20 of 1. And so with this here, that whole inside here, we have to remember that this is saying 20 to some power equals 1. Well, that some power has to be 0. Because 20 to the 0 power would be 1, and 6 times 0 is 0. Number 11, we do need to work the inside first, so let's see if we can simplify the inside. And again, this is a good situation where we can just focus on our base to a power. So 16 is 2 to the 4th. 1/4 is really 2 raised to the negative 2. Negative because we need reciprocal, and then 2 because 2 squared is 4. And so on the inside here we have negative 2 over 4, or negative 1/2, and that's raised to the 3rd power, which is going to be negative 1/2 times negative 1/2 times negative 1/2. So that's all going to simplify to be negative 1 over 8. For number 12, we need to change our exponent here, or the root, to an exponent. So we're going to have negative 8 times log of 10 raised to the 1/4. And so we're going to have negative 8 times, and keep in mind, if there's no log or no base written, it is 10 to the 1st, and this is 10 to the 1/4. And so using our nice little shortcut that we've learned, that means that that is going to be negative 8 times 1 over 4, which is going to give us negative 2. Number 13, we need to do some rewriting inside here. So that's going to be the natural log of e to the negative 2, and we will move the negative 2 to the front. So that's going to be negative 2 times natural log of e, and the natural log of e is just 1. So negative 2 times 1, or just negative 2. Moving on to 14. 14 is another property, and that property tells us that if we have this base and this understood base up here to be the same, then our solution is always sitting there. So here on 14, my answer should be 4. And finally, number 15, we are going to simplify the numerator and then simplify the denominator. Well, log of 10, remember that base is 10 if it's not written, so log base 10 of 10 is 1 over natural log of e is also 1. So all of this simplifies to 1. Now we're going to look at solving logarithmic equations. And sometimes we have to expand and condense problems, and sometimes we don't. For number 16, we don't on this one because we have a single logarithm on one side. And so what we're going to do is we're going to remove that logarithm by taking our argument, 3x minus 2, and we're going to say that's equal to this base raised to this power. So it's going to be equal to 4 squared. And so we have 3x minus 2 equals 16. And if we solve for x, we need to add 2 over to the other side. So 3x equals 18, so x is 6. And we do need to check to make sure this does give me a positive value back up here. And when we plug in, we have 18 minus 2. So yeah, that should be positive. Okay, for the next one, number 17, same process again. We don't have to worry about condensing anything because it's already put together. So what we're going to do again is we're removing the log. So we're going to have 5x plus 14 is equal to x raised to the second power. Now what we have is a factoring situation. We need to move all of our variables over to the other side. So we have x squared. I'm going to subtract 5x, subtract 14, and that's all equal to 0. And we need to factor this. We're going to get x minus 7 times x plus 2 equal to 0. And then we need to set each part equal to 0 and solve. So we have x equals 7 and x equals negative 2. Now we do need to check again to see, are we going to get negatives in the places that we need to make sure we don't have a negative value would be here and here. And notice if I plug in negative 2, I will have a negative value in one of those two places. So that needs to be tossed out. But be careful, we can't assume every negative value gets tossed out. It just depends on the problem itself. So the answer here, that final answer, would be x equals 7. Moving on to the next example, this is a great place where we do have to condense our logarithms before we try to solve. And so with subtraction, we do condense that to division. So I have log 2x minus 1 over 5, there's our division, is equal to 0. And do remember the base is 10 if it's not written. We are removing the logarithm here, so we're going to have 2x minus 1 all over 5 is equal to 10 raised to the 0 power. So that means we have 2x minus 1 all over 5, and 10 to the 0 power is 1. And we need to multiply both sides by 5 to remove that fraction. So I have 2x minus 1 equals 5. We're going to add 1 over, so 2x equals 6. And finally divide by 2, so x is 3. Now we do need to go back up and make sure if we substitute 3 in for x, we don't have negatives. And we won't for this case, so x equals 3 would be our final answer. These problems, 22 through 24, this is a great example of where instead of like earlier, we're able to get the bases to be the same on both sides. With these problems, we would not be able to. So what we need to do is take the logarithm of both sides of our equation. So I have log 4 to the x equals log 20. And the reason why we do that is so we can use our rule that tells us we can move this x value to the front. So we have x log 4 equals log 20. And then our final step is to divide both sides by log 4. And so we are going to, on this test, leave these in exact form. So x equals log 20 over log 4. And that would be your final answer for this one. Moving on to our next example, again another case where we are not able to get our bases to be the same on both sides. So we can start out by finding the log of both sides. So we're going to have log of 2 to the 3x plus 5 equals log to the 6 2x minus 7. After we've taken the log of both sides, we can move our exponent on both sides down to the front of our equation. So we're going to have 3x plus 5 times log 2 equals 2x minus 7 times log 6. And so from this point, we're going to have to use our distributive property because our x values are inside of our parentheses, and so the only way we're going to have is to do the distributive property. So we're going to have 3x log 2 plus 5 log 2 equals 2x log 6 minus 7 log 6. After we have this, then we're going to put everything that has an x on one side and everything else over on the other side. So I'm going to move my 2x log 6 to the left, but then I'm going to move my 5 log 2 over to the right side. So I'm going to have 3x log 2 minus 2x log 6 equals negative 5 log 2 minus 7 log 6. After we have this, notice we do have a common factor of x in both terms here. So we are going to factor out that x. And when we do, we're going to have left over inside the parentheses 3 log 2 minus 2 log 6. And that's equal to negative 5 log 2 minus 7 log 6. And then finally, since we're solving for x, we're going to divide both sides of our equation by what's inside the parentheses, and that will get our x value by itself. So I'm going to divide by 3 log 2 minus 2 log 6, the left side, and we'll do that over here on the right side. So again, 3 log 2 minus 2 log 6, and that's going to be our final answer. We have x isolated on one side, and then all of this other gobbledygook over here, this will be our final answer, and you can leave it just like that. For number 24, what we can do first is, since our exponent in question is right here, all of that is e to the 2x minus 3, we can go ahead and divide both sides by 3. So that gives us e to the 2x minus 3 equals 5. Now the difference with e is we're going to do, instead of the log of both sides, we're going to do the natural log of both sides, because the natural log, that's just an abbreviation for log base e. So that's going to help us here because I can still move my exponent out to the front. And so I'm going to have 2x minus 3 times natural log e equals natural log 5. And so we're going to apply the fact that natural log of e is 1, and 1 times 2x minus 3 is just 2x minus 3. And that's all equal to the natural log of 5. And we are going to solve for x again. So we need to add 3 to both sides. So I have 2x equals natural log 5 plus 3. Please don't add the 5 and 3 because they're separate values. And when we divide by 2, make sure you put the entire right side over 2. So we end up with x equals natural log of 5 plus 3, all of that divided by 2. Alright, so for this question, we're going to go through and use our general formula that told us that our final population is equal to our initial population times 1 plus our rate. And that's going to be raised to our full time period divided by n, and n is the number of times your rate occurred over our given period. So for this problem, notice that we're told that a new teacher makes $30,000 and each year his salary is increased by 5%. For A, they want us to write the salary as a function of time. So here we're going to have our final product, our population, times our initial value, which is going to be our 30,000, times 1 plus our rate. So 1 plus, and our rate needs to be turned to a decimal. So we had 5% increase, so this is an exponential growth of 0.05. And this was going to be over a time period, and we were not given really a time period, so to speak. So we're going to have that as t over n, because our n, this rate occurs each year, so n would be 1 here. All right, for part C, and we've skipped part B, part C says to determine what year of teaching the teacher will earn at least $100,000. Salaries are established at the beginning of the year. So I'm going to move down to the very bottom of the page, and we're going to work out part C here. So we're looking for what year, so we're looking for X, will we finally have $100,000. So we're going to set 100,000 because that's really going to be our final product. So 100,000 has to be equal to 30,000 times 1, and if we go ahead and add our rate, that's going to be 1.05, and that's going to be raised to X, because X is going to be our time period. And so here we need to solve for our X. So the first thing we do would be to divide both sides by 30,000. And remember here, we can reduce this quite a bit by removing those zeros. So we have 10 over 3 is equal to 1.05 raised to the x. And now again, we're solving for x, so we're going to go through and do the log of both sides so we can move our x value down to the front. So I'm going to have log of 10/3 equals log of 1.05 raised to the x power. And then from there, we're going to move our x to the front. So that means that I have log 10/3 equals x times log of 1.05. Move my screen over. And finally, to solve for x, we would divide both sides by log of 1.05. And this is where we would need to use our calculators. So it looks like x is going to be equal to, so that means that we're going to get right about 24.6765 years. So roughly to our nearest year, we're going to say that's going to be in 25 years, just in time for them to retire. In Part D, we're asked to determine how long it will take the teacher to jump from at least 50,000 to at least 75,000 per year. So in Part D, we would be using our graphing calculators for this. So the best way to do this problem would be for us to go ahead and graph our given equation. So in Part D, the first part, we would need to graph our equation, and that wouldn't be anything different than what we are used to doing. So again, we would graph the 30,000 times 1.05 raised to the x power. And then the second part, to really find this, we could use our trace feature or the table feature, either one, to find those values. And for our last problem, we're given the price of a computer is decreasing at an exponential rate. In 1985, a desk computer cost $2,500. The price of a comparable computer is decreasing by 3.5% every 2 years. During what year is the price of that comparable computer $1,200? So we need to go ahead and label our variables for this one. And we are using our formula P equals P sub 0 times 1 plus our rate and time over N. So notice that our final population is going to be $1,200. The initial population of this problem is going to be $2,500. This is our starting price. The rate at which our computer is decreasing is going to be negative 0.035%. And now let's talk about our time and our N. N is going to be related to our rate. So how often does that rate occur? That rate is going to occur every 2 years. So N in this problem is going to be 2. And then T is what our variable is going to be. We want to know at what time does this all happen. So let's go ahead and set up our problem. We have 1,200 is going to be equal to 2,500 times, and now we have a decreasing rate, so it's going to be 1 minus 0.035, and that's going to be raised to the time over 2, because again in this problem that rate occurs every 2 years. Alright, so solving this, the first thing we need to do is to divide both sides by 2,500. So we'll go ahead and take care of that. And then notice that we're going to have 12 over 25. It's going to be equal to 1 minus 0.035 raised to the t power. And this is where we're going to need to do our log of both sides. So we're going to have log of 12 over 25 is going to be equal to log of 1 minus 0.035 raised to the t power. So we're going to have, and I wouldn't worry about separating or any of this because we will type all of this final information into the calculators. Now we do need to move our variable time to the front, and so that's t times log of 0.965. I'd go ahead and subtract those. And then finally we need to divide both sides by log of 0.965. And then over here this side log of 0.965. Hey, I just realized I did not bring down this divided by 2. So let me go back and fix that. Divided by 2. And so we would multiply over here by 2. And when we put all of that in the calculator, we should end up with 41 40.20 years. And remember, the question itself said during what year. So let's see, our original year, we started out in 1985, and we're going to add to that 41.2 years. So it looks like we're going to end up in year 2026.2, but we're going to just round it to the nearest year.